So I've got this little guy here of E little xk, comma k. Right? So I said that each one of those guys is assumed to be in my F, you know, and intersections of guys in my F are also in F, and so this is in my sigma field F because these guys are. All right. So I can make sense of that. And what's the probability, everybody? So this is something you should be able to write down. You've got a Markov chain, the countable state space. I've told you the initial probability mass function, and there's a transition matrix somewhere. So you can all write down that probability. Yeah? What is it?
Mu of x0.
Mu of x0.
We have to use our old friend, the transition kernel.
Yeah, well, here it's a matrix, but yeah, because it's countable. But yeah, I mean, you can still call it a kernel.
Yeah.
So I got it. So it's equal to, it's a long equal sign. You said mu of x0. Did I call it mu 0 of x0? Yeah. And the probability of going from x0 to x1 and so forth. And that's n minus 1, yeah. Okay. And so this extension theorem I referred to is that, you know, basically once you define the probabilities in all these simple events, then you can extend it to all events in quotes, but all is not everything. I mean, there's restrictions on how big F can be, but F's a sigma algebra, and I've defined a probability measure in every simple event. I can extend it to some sigma algebra, and maybe I'll have to tell you which one that is. Yep.
What if, so your random variable was x k omega equals omega k times omega k minus?
You can't multiply these things together. It doesn't. No, capital omega is some abstract nonsense set. You know. Yeah. There's no computations in omega world. That's you know, that's the land of the dogs, the great dogs.
So you would not be allowed to do that. Like, what would?
No, that doesn't make sense. No, everything's over here. Everything's here in. That's the world we live in. You know, omega's a fairy tale land, you know, invented by.
It would just be because it's like it would just be another omega.
Well, it doesn't, you can't multiply. There's no operations in omega world. It doesn't make.
Okay.
Yeah. Well, there is, which I'm about to get to. I'm about to talk about one operation in omega world.
But instead of looking at it as omega k times omega k minus 1.
There's no times. But
like I'm saying, like that's just another omega.
There's no multiplication anywhere.
Well, yeah. But why think of it that way?
No. This is. I'm just saying. I'm just bringing you the wisdom of Russian mathematicians and amazing American Russian mathematicians since in French, and yeah, this is just the only way I know how. The only language I have for talking about these problems. I better say it. We're going to take F to be the smallest sigma algebra. Did I say that's called a sigma algebra? F is called a sigma algebra. Forgot to say that. Algebra. Sorry about that. It's called a sigma algebra, a sigma field. Both terms are used. They mean the same thing. It's pretentious sounding language. I'm sorry. I wish it was just called the domain of P or something. You know, it's the domain of P. That's really precise. That's what it's supposed to be. Now this Borel sigma, just don't worry about it. It's the smallest of all sigma algebras containing the elementary sets. I will need this, unfortunately. You'll see in a minute. So EXK. the definition of a Borel sigma algebra depends on the context. In this case, I'm looking at a countable state space. These are my elementary events. And there's a notion of the smallest sigma algebra containing those elementary events. And what that means is that you take all possible sigma algebras that contain all of these elementary events, and the intersection of sigma algebras is itself a sigma algebra. And you take the intersection of all of them. I know that's crazy, but there's a notion of smallest, and you don't have to understand it. It's just when I say smallest, I mean that, okay? You can make it very precise by, again, taking all sigma algebras containing the elementary sets, intersecting them all, and prove that's also a sigma algebra. All right? So I'll say Borel, and I'll remind you it's smallest. So why do this? You will see. I'll just jump to it. The reason for doing this is because it's a way we end up using the same idea for getting an idea about information. So I'm going to define Fn to be the smallest sigma algebra containing these sets containing x and xn, but k only less than or equal to n. And so a set here is something that I can express in terms of what I've observed, up until this time, See, so when I write the probability of A with A and Fn, I forget, I don't need the probability. When I write A as an Fn, then A is actually equal to the set of omega such that x1 of omega dot 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 xn of omega is in some set So a set A in Fn can be represented by some set, the event that the sequence up to this is 0 there, isn't it? That the sequence up to time n is in some set SA. It's the same thing, and that's why Fn is considered the information up to time n, because it's all the things that I can actually, I've actually observed up to time n. So it's a way of modeling it. We'll see. It's going to take some time, or if you've taken a course with me before, you've seen it. That it's a way to model information. That's a bit vague, but I'll try to make it clear as we go along. All right. I almost didn't do this, and I forgot that there is a reason, because it makes things more concrete and simple to describe. What time is it? By having this explicit construction, you can express the Markov property in a different way, and from that you get this thing called the strong Markov property, which is super cool and useful for analysis. Okay, and here's a big idea. So this is just a notational treasure, as we'll see. And what it does is so trivial, it's ridiculous, but you'll see it's valuable. Theta k hitting some omega, so I'm not going to put parentheses around it. So I take an omega and I hit it by the shift operator. Guess what it does? It just shifts it. It just throws away the first k elements. That looks like a joke, I know. And then, okay, so anyway, so there's a definition. There's a shift operator that just takes a sequence, and, you know, in this sequence space, chops off the first k elements and gives you the rest, all right? And then you extend that to random variables. So if h is a random variable, it means it's a function on omega, right? And so when I say theta kh, well, it's not that. I'm extending the definition. So first I define an operator in sequences. Now I'm going to define something that maps random variables to random variables. And what does it do? So this is a new random variable. If I evaluate then at omega, so maybe I should put brackets around this. I take a random variable, I hit it by the shift operator, and that's a new random variable, so I have to tell you what it is at omega, and what do you think it is?
You're shifting the argument.
Yeah. All right. Okay, so why on earth would I do this? Why on earth would I do this? So let's do some examples. Let's say, here's an example. Okay, so we always suppress the omegas when we write down random variables, almost always. So xk is a function of omega. But remember, in this explicit construction, xk of omega is just omega k. It's the same thing. Right? And then somebody tell me what, I should go k, n, something else. So what's theta kh evaluated omega? I'm not going to always put in those brackets. I mean, there's a bit of extra space there just to say I'm shifting and then I'm evaluating. I'll put brackets in one more time. What is it? So h is a function in sequences, but it's just a function of the nth term in the sequence.
Just be h of omega n plus k.
Yeah. I'm shifting the whole thing and then I'm ripping out the elements. So it's just that. Okay, cool. So so then there's this really cool result. And let's go through this. I've got everything set up here. Look at that. And I want to put all this together. Yeah. So given this, let's put it here. What is the conditional expectation of theta k h given fk? So I'm still in the same example, haven't finished yet. Well, who knows? Because it's too abstract to even think about. So, the first thing you have to do is you have to take this and plug in what it actually means. Because this is actually h of xn plus k. All right. So plug it in. All right, the information up to 10k. And what's that, everybody? Let's expand it out so it's clear. Oh yeah, forgot the x. Okay, so here it might seem like I'm cheating, but I'm just reviewing stochastic processes. So if you take a course in stochastic processes, you make this definition, and whenever you write this, what you really mean is that. It's the definition. It's the same thing, So when I've been saying this over and over again, conditional expectations, without defining it, so just assuming you've taken noise with stochastic methods too, but when you write this, you mean this, and that's same thing.
Can you explain how the conditioning went from f sub k to f sub n here?
Oh, did I make a mistake? Oh yeah. Excuse me. Sorry. All right, but yeah. So when this notation's identical. It's exactly the same thing. Okay. And what's that? P to the what? To the n h of x evaluated at x equals xk. So as you saw in the homework, we all know conditional expectations are some function of the data, and there's the function of the data. Wait a second, that's not what I wanted to... No, there's a mistake. Wait, hold on. That's right. Oh, yeah, hold on. There's one more thing I want to say.
What does that x equal to xk mean? Xk equal to x, right? What is the...
No, it's just that, again, it can be really confusing. I take h, I hit it by pn, and I evaluate it at x equals xk. So I'm just trying to emphasize that is a function of the state space, right? And then I get a new function, I evaluate at xk. I didn't even see that I left out some notation, maybe.
Greater than 1, wouldn't that be like useless information?
No, I'm trying to, there's a bit of, no, please, that's not, hold on. I'm not trying to tell you something new. I'm trying to come up with really some valuable notational conventions. So what is this again? This is a conditional expectation of let's write it down again. It's h of xn. I'm going to unravel this again. Let's just keep unraveling this. So when I write p to the n h, I also mean that. All right, it's the same thing. And what is that? That's h. H was just h of xn. And now I really regret not introducing some notation earlier, but so I forgot to introduce this first. There's this more compact notation where you write expectation sum x, where you say I initialize with my Markov chain at x, and then take the expectation, or I can initialize at mu, and then I write e sub mu. All right. So what this is, in this notation, what we're saying is that this is expectation sub xk of h. And that's the Markov property. All right, so let me summarize that. The expectation, I'll write this really carefully, of theta to the k, h, given fk, is equal to, and it doesn't matter what mu was, right? I mean, the initial distribution is not important. When I computed this conditional expectation, I didn't care how x0 was distributed. The last state value is all that matters. So here I don't need to tell you anything about the initial condition. But this is equal to the expectation sub xk of h, period. And that's for any random variable. So I went to improve this for you for the special case where h was just a simple function of the Markov chain at some time xn. But I didn't have to. It could have been anything. The same argument would have gone through. So that weird thing about having e sub random variable of h is incredibly useful. Okay, I'm going to use it a lot in the next weeks. You know, I think I'll still be using it in April. So one more thing in your flashcards, I'm afraid, right there, flashcard. I swear to God, I swear to God, I think the flashcards, the required flashcards will reduce as we go along. You know, it's going to go down exponentially fast. But there's another thing you really have to remember because I can use it a lot. Okay, so that's the Markov property. So we should take a break now because this is just a convenient way of writing things down. But there's something way more powerful that's the next step forward, and that's the strong Markov property. So that's what we'll do in an hour or two. Okay.